All of the footage in this video has been declared unclassified by the Department of Defense and the Strategic Defense Initiative Organization. The footage you are about to see all comes from the Pentagon's official files on SDI. Our purpose here is not to enter into a political discussion, but rather to concentrate on the technological challenges of SDI and how the scientists and engineers are making Star Wars a reality today. In this first video on SDI, we will take a broader, more systems view of the total Star Wars architecture and how each piece must fit into the system.
I'm still optimistic that a way will be found. The door is open, and the opportunity to begin eliminating the nuclear threat is within reach.
When first announced in 1984, many people said it couldn't be done, the universal cry met by every new idea. But a few dedicated men and women in and out of the Pentagon believed differently. This is their continuing story. Before we begin, we should warn you that this video contains more acronyms than you can count, and a lot of jargon you may not understand. Acronyms are words formed by the first letters of a phrase, like HEDI, which stands for High Indo-Atmospheric Defense Interceptor. It speeds up communication, but if you don't understand the meaning, you're lost. To make it easier and save us the time of explaining things, we've included a complete printed glossary of SDI acronyms and terms with this video. SDI is extraordinarily complex, with literally dozens, perhaps hundreds of programs. We've divided the video into several major segments to help us understand and organize Star Wars. First, we'll look at the threat. Originally envisioned as protection from a massive Soviet attack, today's threat comes from regional and theater weapons in third world nations as well. In order to understand SDI, we need to understand the architecture of how a missile attack works and what kind of windows of opportunity exist during the 25 to 30 minutes from liftoff to impact. The character and vulnerability of an ICBM changes dramatically during flight as it goes from boost to mid-course deployment to terminal phase. At that point, we'll look at the history and background of SDI to put the whole program in perspective. Next, we'll check out the overwhelming challenge of ATP. In other words, acquisition, tracking, and pointing. Whether you're looking up into space with the sun as a background or down at the Earth with all its infrared interference, to find and track a target is very demanding. Then there's C-cubed, command, control, and communications. With all the sophisticated jamming systems around, how do you keep in touch? Here's a hint. Use a frequency that can't be reached from Earth. After identifying the target, we'll look at destroying the missile and its warheads. As we look at Phase 1, we'll see how we went from smart rocks to brilliant pebbles and how to hit a bullet with a bullet. In space, the delivery systems are unbelievably complex, but the warheads are kinetic. They carry no explosives of any kind. None. And finally, we'll take a look into the future at Phase 2. This is the real Star Wars. Speed-of-light weapons, neutral particle beams, ground-based lasers with free electrons using fighting mirrors, hypervelocity guns that accelerate to 10 kilometers per second at 100,000 Gs. Remember, everything you see in this video is real. It's happening today all over the world. From Lawrence Livermore Lab to Kwajalein Atoll. From Ground Zero, as the center of the Pentagon is called, to Edwards Air Force Base. The likelihood of a massive first strike from the Soviet Union is less today than in the past, but that does not eliminate the threat to American troops and interests in the world. Today, the greatest risk may come from the third world. There are 8 countries with missiles right now, and most have or are developing nuclear weapons. Afghanistan, Iran, Iraq, Israel, Saudi Arabia, South Korea, Syria, and South Yemen have missiles in service with ranges up to 2,700 kilometers. These other countries are testing or in development of missiles from North Korea's 300-kilometer Scud-B to Iraq's Tamaz-1 with a range of 2,000 clicks. As you can see, these missiles reach well into Europe. The CIA estimates that by the year 2000, over 15 developing countries will be producing their own ballistic missiles and arming them with nuclear, chemical, and biological weapons. The threat of massive U.S. retaliation may not be a great deterrent to some of the off-the-wall third-world dictators. The only protection is a defensive one. You simply have to knock out the threat. Today, the United States has no active defense against missile attack. And finally, there is always the chance of an accidental missile firing. Today, it probably wouldn't lead to World War III, but as the old joke goes, a nuclear bomb can ruin your whole day. To defeat a ballistic missile, you have to understand how it works and how much time you have. The lifespan of a ballistic missile is only 30 minutes. In that time, it gets up and out of the Earth's atmosphere and goes through 3 distinctive phases. In the first phase, which includes both boost and post-boost, the missile is leaving a white-hot plume, and it's carrying all of its warheads in one platform or bus. A single intercept can take out all warheads with one blow. The problem is, boost only lasts 4 minutes, and post-boost lasts only another 10 minutes. Only 14 minutes to detect the launch, acquire the target, track it, and hit it. At mid-course, the bus, which carries all the warheads, releases up to a dozen live warheads and hundreds or even thousands of decoys. The trick, of course, is to distinguish between decoys and the real RVs, or re-entry vehicles. SDI has 13 minutes during mid-course to sort all that out. While most decoys are nothing more than mylar balloons, in the vacuum of space, they behave very much like RVs. To make matters really interesting, there's a good chance that all this will take place in a nuclear environment caused either as part of an enemy strategy or as the result of previous intercept. The RVs begin their terminal phase when they begin to pass through the atmosphere. In one way, that makes things easier. The atmosphere burns up and strips away all the decoys. But there are only 3 minutes left to impact, and the nuclear warheads are coming almost straight down at several thousand miles per hour. Put all together, SDI has less than 30 minutes to detect the launch vehicle, acquire the target, track it, discriminate the decoys, point, and fire. As early as 1984, SDI performed a successful mid-course intercept, hitting a bullet with a bullet. In 1985, SDI demonstrated that a laser could destroy a ballistic missile booster case. In 1986, as part of the Delta series, Delta 180 intercepted a thrusting target in space. As amazing as these feats were, in many ways, those were easy tasks. The real challenge is creating a system, not just a single technology. A system that cannot be overwhelmed or defensed with a single trigger. As with any research program, many ideas were explored in the early days. One possible solution would be the use of nuclear warheads, which, like horseshoes and hand grenades, only had to come close. There was the idea of huge lasers planted in space that could hit boosters, buses, and warheads with the speed of light. Both ideas have fallen out of favor. Nuclear warheads might create more problems than they would solve by generating an environment so alive with infrared and other energies and frequencies that nothing could be seen by SDI sensors and seekers. As for space-based lasers, in order to get the power needed for lethality, a space-based laser would have to be so big that the cost of boosting it into space in quantity would be prohibitive. Plus, having only a few such stations would make them vulnerable to enemy attack. So over time, SDI has become more streamlined and elegant. The need to acquire, track, and point at incoming missiles in all their stages, all their phenomenology, and against the background of space, the sun, the earth, and the Van Allen radiation belt has remained unchanged from the beginning. So has the need for massive, radiation-hardened, nuclear-hardened, jam-proof computers and communication. Phase 1, however, has come to focus on boost and post-boost, as well as mid-course defense. In both cases, we are looking at KEWs, or kinetic energy weapons. The KKVs, or kinetic kill vehicles, carry no explosive warheads of any kind. More on that later. Phase 2 focuses more on the mid-course and terminal threat through the use of DEWs, or directed energy weapons. These are speed-of-light weapons involving such technologies as neutral particle beams, free electron lasers, and chemical lasers. When you think of SDI, the first thing that comes to mind is impacting enemy missiles and warheads in space with bombs or laser beams. The biggest challenge to SDI may not be hitting a target. It's finding it and tracking it. ATP-FC is acquire, track, and point.